The broadcast is now starting. All attendees are in listen-only mode.
Good morning, good afternoon, everyone. My name is Dr. Susanna Gyenes, and I would like to welcome everyone to this complimentary webinar today. Today's topic, as you could see in the registration form, it's a taxonomy of hydrogen incidents and how to, how to design safer plants. And I am very happy to be here with Mr. Laurentiu Zamfirescu, who will be your presenter. I will introduce him very shortly. First, I would like to tell you more about how the webinar is going. My name is Dr. Susanna Gyenes. I am the deputy to the IChemE Safety Center's director, and we have these complementary webinars on different topics with our IChemE Safety Center member companies, and that's why we are so delighted to welcome AMOG Consultancy here in this webinar. After the presentation, you will be able to ask questions, and feel free to type your questions in the meantime in the question box, and we will try to answer to your questions in the end. And you will be able to watch again this webinar on our YouTube channel and other forums I will be talking about in the end of the presentation. Let me introduce now Mr. Laurentiu Zamfirescu. He's a career risk safety and process safety engineer with close to 15 years of experience. He currently works as a consultant for AMOG Consulting in a lead engineering role. His previous experience comes from regulating major hazards facilities, Seveso and Coma sites, both in Europe and Australia. He is a professional process safety engineer with IChemE, a chartered engineer with the Safety and Reliability Society, and a certified functional safety engineer. Laurentiu is also an active contributor to the IChemE Safety Center and other similar organizations advancing process safety worldwide, volunteering for the development of publications and other resources. Before he gives his presentation, I briefly would like to introduce you to the IChemE Safety Center. So here you can see that we have the IChemE Safety Center have many operating and industry partners who you see on this slide. We are very proud of having our partners working together with us in advancing process safety worldwide. As you can see here, we have such a wide variation of companies joined us, and we are working towards publishing really interesting and useful practical guidance documents, interactive case studies. I will give you a full picture in the end of the presentation. What are our publications, and where you can reach those publications. We also work with a lot of supporting partners and collaborators, and they are coming from regulators and different universities worldwide. And I will be talking about those publications that are really valuable, that we are working together with our supporting partners and collaborators as well. And this is just another overview who we are working with. You can see here breaking up all these members into industry types. It's not only oil and gas, but it's utilities. We have a wide range of consultants and insurance companies joined us, pulps and paper, mining, chemicals, and so many others. Before we go into the details, just want to let you know that the IChemE Safety Center works around a framework for process safety. It is not a process safety management system, doesn't even seek to replace one. However, our company members decided that they would like to work around this framework because it overlooks the whole process safety range. What does it mean? So you can see here the 6 elements: systems and procedures, engineering and design, assurance, knowledge and competence, human factors, and culture. And all of these areas are underpinned by leadership. And leadership is crucial. It's crucial in every element, and it is crucial at every level within the organization. So this is how we frame our guidance documents and how we work towards in the way and the path of process safety. And now I would like to give the floor to Mr. Laurentiu Zanfirescu to present on hydrogen safety. Laurentiu, please.
Thank you, Susanna, for the introduction. Thank you, everybody, for attending, and hopefully you gonna get the knowledge you are hoping for and the information you are seeking when you join. So before we proceed with the presentation, I'd like just to provide a very high-level overview of AMOG. So AMOG stands for Australian Maritime Offshore Group. That's where the roots of the company started about 25 years ago. It's an Australian-owned and based engineering company, and we specialized in solving complex, challenging engineering problems. We have about 50 engineers, and these are split around our offices in Australia, in the US, in the UK, and Colombia. Our main service area are marine and offshore engineering, where we're talking about naval architecture, moorings and risers, subsea engineering, failure investigations, integrity management, as well as assisting in concept design. Then we have our structural engineering group, which looks after assessment of structural integrity, condition monitoring, fatigue and fracture mechanics, forensics assessments. And this is all coupled with a suite of services under Industry 4.0 or Industrial IoT, where we're looking at machine learning and digital twins and instrumentation to assist in problem solving. And nonetheless, the group I am in, which is our system safety engineering group, where we provide a full range of risk and safety engineering study services, from HAZIS to HAZOPS to fire safety engineering, QRAs and consequence modeling, safety cases, hazardous area classification, and anything in between that you may think of. We have a strong capability in functional safety engineering, working on complex continuous demand systems, as well as system safety and process safety management. So some of the sectors we service are also aligned with some of the IChemE members. We work in rail and defense and transport, chemical, petrochemical, onshore and offshore oil and gas, mining, ports, and a few other ones. So that is for a high-level overview of the company. So can you please go back, Susanna? Okay, so the idea of this paper. Okay, I'll click it. The idea of this paper originated whilst we were working on a greenfield hydrogen project from the early design stages. What we found out on that project is that there is not a lot of information that was able to assist us in developing the safety in design plan. So we decided to conduct a review of the various hydrogen incident databases and information sources of it that are available in order for us to understand what we should take into account during the design phase and apply any learnings for that project as well as for future projects. As you see on the picture, that is also a hydrogen project. It's a very famous one. Unfortunately, it didn't go so well. It is the Hindenburg airship. So let's touch a bit on the properties. of hydrogen. So some of these properties that make hydrogen more hazardous than other flammable gases, such as LPG or natural gas, is that whenever we have a release outside of the process equipment, of the pressure containing envelope, the leakage rate is high. It's coupled with a fast diffusion rate and very wide flammability ranges from 4% to 74%. And on top of that, we have a very low ignition energy requirement in order to set off a hydrogen gas cloud. So in other words, to make it very simple and bring it home, hydrogen leaks fast, it fills up the safe quickly, and it's very easy to ignite. That's why perhaps after that Hindenburg accident on which we touched on, not many companies and countries were in a rush to invest in hydrogen technology and hydrogen as a fuel. However, based on the current global environmental challenges and technical advancements, hydrogen has seen an unprecedented interest and growth. Unfortunately, the hazardous properties of hydrogen have not changed over time. It is not any less hazardous, and we still need to manage it appropriately. So for the conduct of this work, we consulted 3 databases. There are other information sources available. However, we focused on these 3 ones as they contained quite a lot of information. They were structured quite well, and they were somewhat easy to use. So the Hydrogen Tools, or H2 Tools, it's an American investment. The HIAD database is driven by the European Commission, and the ARIA database is kindly provided us by the French ministry. So the way we analyze these databases, we try to understand, we thought to understand the outcomes of incidents involving hydrogen release. We wanted to understand the causes that led to these incidents. We tried to look also at the equipment involved, and nonetheless, we were looking at the project lifecycle phase in which the incident would have its root and contributory causes too. So in analyzing the event outcomes, our focus was to determine how often explosions and or jet fires occur. So out of the recorded incidents between the several databases, we found that this is in the range of 68 to 86%. This, if you've looked previously at flammable gas probabilities, if you've been conducting quantitative risk assessments, you will know that this is a very high percentage. And this is based on actual incidents, it's not based on laboratory testing. So the very high percentage is not really unexpected. It is surprising to see, and I say it's not really unexpected because of the hazardous properties of hydrogen. That very wide flammability range, the very low ignition energy required to set it off, and as well as the very high diffusion and leak rate. In looking to understand and to classify the causes of the various incidents, we had a bit more of a challenge, because some of the databases did not provide this information. Some other databases provided both the root cause and the contributory cause. There were several incidents, there were several root and contributory causes associated with the incidents, and to make it worse, these causes did not match between the different databases. In some cases, some of the records were not of much use either. They were telling us, well, it's equipment failure or it's loss of containment. Well, we know that. So quoting Trevor Kletz is similar to saying falls are caused by gravity, which is not really helpful for us to in the conduct of a taxonomy. So we sort of changed track when we saw what the databases were providing us in terms of being able to track it down to equipment, or being able to track it down to the actual root and contributory cause. And we were able to classify them by project lifecycle phases to which they have the root and contributory causes to. This works well with the fact that the hydrogen industry is ever expanding, and our interest was primarily to understand how important design is and what can we learn from these incidents. Unfortunately, we were unable to classify all of them in this way, as they are recorded differently. Each database is set up in its own ways, and sometimes the incident investigations were actually in French, and none of our engineers come from a French background. So what we found out is that there is some variability between the databases, but not that much. The findings in terms of the percentages of incidents attributed between design and operations is quite consistent with other industries. So Kinsey and Rowland looked at the aerospace and nuclear industries, where between 51 and 46% of incidents were attributed to design. And Hale looked at generically on all projects and found out that overall it ranges between 20 to 60%. So what are the conclusions of these taxonomies? So, well, we knew that hydrogen catches on fire easily. We did not know how easily it is for an actual release to explode or create a jet fire. So actually having some percentage probabilities was very useful, specifically when we conduct seal determination studies for these sort of facilities. We have some grounding data. So if we think of the conclusion that design is responsible for between 40 to 50% of incidents, well, that leaves us with between 50 and 60% of incidents rooted in the other life cycle phases outside of design, and that is procurement, fabrication, construction, commissioning, operations, maintenance, and why not perhaps even decommissioning. So to deal with all of those situations, there are a number of process safety management frameworks. Some of these do touch on the procurement and construction and commissioning phase. Some don't. Some touch on project management, others don't. But we will not go over each of these frameworks, as the purpose of our presentation is the design phase. So in Australia, for most process plants and complex systems, which cannot be covered well by prescriptive standards, a goal-based performance outcome focused safety legislation applies. So what these regulations require us is to essentially manage risks in a way that they are eliminated, and if not reasonably practicable to eliminate the risks, then so that they are reduced to so far as reasonably practicable. The UK follows the same system. Singapore, from what I remember, follows the same system. So in applying these principles, it comes with a hierarchy of controls principles, which just provides more information to those principles of elimination and substitutions and putting in engineering controls before we go to administrative or personal protective equipment. So those regulatory requirements formed also the basis for developing our safety and design plan. So remember when I provided in the beginning a reference to our system safety engineering work to those other sectors that we service, such as defense and rail and transport. Well, what we found out and we know is that those sectors actually seem to manage technical safety better than the processing sector. You may know of terminologies such as system safety and requirements management, independent safety assessment. So what we've done, we've taken those internal learnings from the various other sectors that we service, and we've put them into application to develop the safety in design plans for the various projects we've been working on. So I'd like to address a question to you, and we will use the chat box for this. What does the term safety in design mean to you? There are various answers from different people, and it would be something very good to explore. So if you could please provide your answers in the chat box, and Susanna will read them out for me. Thank you.
Okay, here we have a few already who replied. Inherently safer design, eliminating hazards while possible to do so. Safety in design equals to design out and address hazards. Anyone else who would like to share? Inherently safer design. Super design, making the subsequent risk assessment very easy. That's another one. Please feel free to drop your thoughts here. Okay, making a process safe from the start. Safety in design embeds risk elimination by designing out hazards by selection of materials, processes, and so on. Cost-effective, inherently safe, future-proof. Identify and mitigate hazards. These are so far that we have. Okay.
Okay. Thank you very much for that. So there is one answer which I'd like to talk about from Nigel Khan. Safety in design is systematic assessment of design through early and continuous assessment of safety. And I would tend to agree with Nigel on this one. So what we've learned from all these other industries is that safety in design and good design does not happen by accident. You need to have a plan in place, and you need to follow a systematic process in order to achieve a safe design. Inherently safer design, it is a methodology that we would apply in these cases. So coming back to the idea that safety in design requires planning, and it is a process that you follow throughout the design process. This is a diagram, a flowchart that you may want to consider as to how would we be able to accomplish safety in design, and how we apply this technical risk management to achieve that. So first of all, we need to have a number of safety management systems in place that will help us achieve that. This is our right-hand column, and there obviously we need to have a risk management framework which talks about hazard identification, about our risk tolerability criteria. Then we need to have a system in place that we actually know and are able to track actions that we raise from the various studies, and we're sure we close them out. We have design gate review stages, i.e. we haven't closed out the HAZOP actions, we cannot go forward. We haven't conducted a LOPA, we cannot go forward with the project because it would be too difficult afterwards to do it. If we want to go back in the project and make some changes, we need to have management of change processes in place so we control it, documentation, control, quality assurance, and so forth. Then there are a number of studies and reviews, to say so, that we will be conducting during the design. Some of these, and these have been tailored to hydrogen and to hydrogen projects, and from seeing the very high propensity of hydrogen to catch on fire and lead to fires and explosions, then hazardous area classification and management of ignition sources, as well as the fire safety study, would be some very important one. Functional safety, as it could be with any complex project. And then let's not forget that we can do all the risk assessments we want. However, the basis should always be conformance to standards, as these standards hold cumulative knowledge of many people over many plants, over many years of operations, which we may not be able to identify through hazard identification, risk assessment, and obviously regulatory and compliance. So now if we're looking at the actual technical risk assessment process that we would follow, we start as always with hazard identification, being hazards, BHA, HAZOPs, and so forth. This will provide us a hazard register or a risk register that we take with us along the entire life cycle of the project, which actually gets passed on to operations and so forth. Now, once we've identified our hazards, we screen them out, and we identify those scenarios, major accident events, if you want to call them so, those scenarios that really concern us and where we should focus our design efforts on. Those are usually the scenarios that live in the functional safety space and will require us to implement safety instrumented functions. Once we understand all of these items, we move forward to analyzing both the consequences and likelihood of the scenario. So whether we're just looking consequence-wise, what are the fires and explosion hazards, and then also escalation, and then the conduct of a quantitative risk assessment. If our project is complex enough to warrant such an analysis, we integrate the likelihood determination. And then once we have an idea of this and we've implemented all of these preventative measures, such as functional safety, hazardous area classification, our fire safety study will help us with gas detectors, with shutdown systems, and so we look on the mitigative side of things. So on the mitigative side of things, we will be looking at occupied building and refuge assessment, so that we're far away enough from where an explosion might occur, emergency response, and fire and gas system. In Australia, in some ways we are required, and it's also good practice to conduct these workshops where we determine if there is anything else that is reasonably practicable to be completed in order to reduce risks further. So this whole process is reiterated as the design matures, and it is being reiterated with each design phase. And we start in concept design, where we may only be able to do a hazard, and then be able to define a high-level fire and gas philosophy. We can, in that one, we would touch on hazardous area classification. We would touch on occupied buildings. After that one, we move into feed. At the feed level, we should already have enough information to conduct a HAZOP and conduct most of these studies. And in detailed design, we will just revise this. So touching on to the management system elements is also how we would manage the safety critical elements through performance standards. And so from the major accident events we've identified. And we can talk a bit more on this one, because I'm sure you would have some questions on it. So coming to the conclusions of this presentation is that inadequate design is responsible for about half of the root and contributory causes for the hydrogen incident. Safety for the hydrogen industry. Safety in design does not happen by accident. This is a process that requires planning and active management. And I also highlight and stress the importance of the word competent engineers in actually having competent resources to achieve this. In many cases, safety planning does not happen. In other cases, when it does happen, it is not systematic, resources are not allocated. There would be perhaps also no assurance process in place that it is actually followed. And then there are the very unfortunate cases where even the term safety in design is a very misunderstood term. And some of the things we heard in our clients' understanding of safety in design spans from safety in design is solely focused on occupational health and safety, i.e. handrails and confined space, etc., to even to the very extreme of it from an EPC, where safety in design is about keeping the engineers completing the design safe in their offices. So there's a lot of misunderstanding. There are industries more advanced than the processing sector in regards to safety and design management, and we should definitely learn from it, because the benefits of a safe design are many folds, and they far outweigh not actually conducting such work. So I thank you for your time. I'll pass over to Susanna, and then you may also write your questions in the chat box and we can cover them at the end.
Thank you, Laurentio, and thank you for this informative presentation, and here you can see also the references to Laurentius' paper. I highly recommend you really interesting sources of information coming from this paper and used for this paper. And especially I would like to highlight, and I'm very glad to see that the ARIA database and the Joint Research Center databases are used, because those are there for free to use. And I always recommend these databases for everyone in every forum I can to promote, because this is where you can get all the information. Plus, the IChemE also has a database by the Loss Prevention Process Safety Special Interest Group, and I'm pretty sure that we will be hearing about that as well from the comments. So thank you again, Laurentio, and also thank you for the clarification of different terms, because that is really interesting to see how people consider safety in design, and thank you for asking the question. In order to add some comments to your final conclusions, which are really useful, you mentioned that you need in every level, and especially in the design phase, competent engineers. So the IChemE Safety Center published many guidance documents. Among them, you can see here the competency one, so that within any organization, what are the different levels of competency, and how to reach those levels of competency around the process safety framework, 6 elements that I talked about in different topics. And then, of course, it's important to be able to recognize how the system works, so that you have to monitor, and there you have available these process safety lead metrics. And that we are talking about design. We also published the guidance document on applying process safety during a concept select phase of a project. This is a very new one, so maybe you will find it very useful. And then you can see all the other publications. I mentioned earlier the education part. We are working towards more guidance documents all together with universities, promoting process safety in education. And also we are working on a guidance document that will be published soon on the passport system. So thank you for your kind interest. Here you can see all the contact details. You can see here Laurentius' contact details. And let me just see what were the questions, so that Laurent, you can answer to those questions. And coming back to the beginning, because I see that we had a question there. How and...
Yeah,
Sorry?
I can read them. Yeah, I can read them. I
all
can
right.
see them.
Go ahead then.
Yeah, so one of the questions in the beginning was how and what quantitative methods have you applied to demonstrate so far? So for Australia, even for Western Australia, there is a recent guideline published in terms of quantitative methods. So the method applied was, and this was depending where the scenario laid on the quantitative risk criteria spectrum, whether it was in the tolerable in the region or broadly acceptable. In some cases, in most of the cases, we did not need to go down to cost and to a quantitative cost-benefit analysis. And in most cases, it was sufficient just to ask the 2 questions of what more can I do and why am I not doing it. And in asking these questions, we would just identify a range of options and then conduct a qualitative determination. In terms of quantitative methods, the UK HSE has established a methodology quite some time ago regarding cost-benefit analysis. The Australian government is providing us a value for statistical life. So when we had to do that, we followed that methodology. I hope that answers your question. Otherwise, you can drop a line. So another one, with the current interest to move to using hydrogen as an alternative fuel, What concerns do you have with increased amount of hydrogen stored in our communities, e.g. in cars or fuel stations? What about the distribution systems? What happens if a hydrogen car vehicle is in an accident? How critical will ignition risk be at the fuel station? How do we design to mitigate against this inherently safety design, etc.? So the ignition risk is, as we understood, it is critical. If there will be accidents, yes, cars may catch on fire, they may explode, as we've covered. What we went here through is a systematic process to be applied in order to understand those hazards, assess the risk, and then make a decision whether we identify it is safe, whether it is safe or not. And this process of this safety and design process is not specific to the processing sector. It is not specific to a plant. It can be applied to anything, as it's being applied in rail and transport and defense and aerospace. I'm interested to know more if there were any commonalities in the design errors. Fiona, unfortunately, the databases do not provide that much level of detail. And as you can understand, conducting an investigation varies, the quality of conducting an investigation varies a lot. And then also the recording and of the incidents suffers, and quite a lot of information is lost in the process. So most of those, from what I remember, except for the French one, most of those databases are voluntary reporting, just for the industry to learn from it. The one from the French government is driven by the COMA regulator, so they get those incident notifications. Are there literature standards available about making natural gas transmissions line ready for hydrogen? Jürgen, I do apologize. I have not worked on such projects, so I wouldn't be able to answer your question. So if I can give some example of design failures that led to serious hydrogen incidents. So the range is great, between 30 to 60, 30 to 60 causes. I can quickly have a look to open some of those, just to read out from them. It shouldn't take me long. Okay, so some of those causes were inadequate maintenance, design fault, abnormal operations, material incompatibility. So material incompatibility is actually quite a high one, which had a number of them. Human error comes again to actually taking into account human factors during design. Hazard not identified in advance, that comes to not planning for safety in design. Inappropriate, inadequate equipment labeling. Some other ones in terms of equipment failure, piping and valves were some of the top ones in terms of equipment that led to failure. Bursting discs, compressors. With the bursting discs, I am assuming it was venting not to a safe location, because bursting discs are quite reliable. Vessel failure, glassware, in case you're using sight glasses for that. Then we had some in the operational stage, situational awareness, which doesn't help much, inadequate inspection, etc. So those are some of the various recorded causes. If we can go back to the reference slide, yes, sure, I can leave the reference slide. Susanna, would you mind answering the question about making the slides available for the PowerPoint, or how this will work about CPD? And I'll read some of the other questions until you provide that information.
All right, Laurenti. Yes, of course. The recording, as I mentioned in the beginning, will be available, and that's what we do all the time with these complimentary webinars. So that is the information about that. And yes, go ahead, please, with the remaining questions. We still have a couple of minutes, and then if you all have more questions, then I'm pretty sure that Laurenti will be able to help you through emails as well, because we have limited time available. Go ahead, Laurenti, please. Thank you.
We only have one or two more questions. So you have calculated ignition probabilities using these databases, but how sure are you that these databases will include all the loss of primary containment events that do not ignite? These events were also included. If we can go back to, and for this I rely on you, Susanna, because I can't go back with my mouse, to slide 10.
Which one, sorry?
10, the one with the table. So go back, go back, go back. Yeah, this one. So as you can see from that one, we have a range of between 68 and 86% of incidents. That does not mean all the incidents. And you are correct, we are bound by the information we have in these databases, and as it is very likely to happen when we have a near miss and the actual hydrogen doesn't catch on fire, or there's no big significant material damage, we tend not to report those. And this is voluntary, it's primarily voluntary reporting for the incidents that goes in this database. So we just use the information we have available, and we make the best use of it as we can. And all of this is combined with appropriate assumptions. The question of hydrogen safety in the user environment is a good segue into my talk coming up, which will discuss some of the lessons we have learned from fuel stations and heating of homes in the UK. If that's done for the IChemE, Susanna, I'm sure you'll be able to share that. So this brings me to the end of the list of questions. So I would like to thank you all very much for the attendance and for the interest shown in this presentation. Thank you again, and Susanna, I leave it to you. Thank you, have a good day.
Thank you, Laurenti, and thank you everybody for your attendees. And as I mentioned earlier, we will put this recording up to the IChemE Safety Center's YouTube channel and LinkedIn and other forums. Feel free to share this presentation with those that you think that may be interested. Thank you so much, and goodbye.